Hi, this is Dr. Graves with the Cal State Northridge Geography and Environmental Studies program. This is a video tutorial, perhaps one of two, that helps students learn how to create a cost curve calculator so you can look at things like the rate of return on a investment that one would hope would repay over time. It can be used for solar as we're doing it here, but there are a lot of other environmental investments that an organization or a family could make that have upfront costs that take time before they can be repaid. And so this is one way of kind of taking a look at this. Solar is more complex than many of the other investments that one might make in sustainable energy or usage of resources, and so it's kind of a pain in the butt to do this, but also if you can do this, you're going to be good for other things like drip irrigation systems or investments in your soil, electric cars, that sort of thing. So we're going to assume, because my class suggested this, that it's just a house system. You can scale this up, multiply the cost and size of the system, and you could use it for a business or a larger interest, like a college or something. So the first thing we really should do is scroll to the right on our spreadsheet here, and I have some of the assumptions that we may be working on, and all of these can be adjusted. Always make sure you double click inside so that you see what has a calculation and which of these things are simply entries into your assumptions area. So what I thought we would do is just go with something reasonably simple because everything else is so complex here, and we will say that our initial outlay here in cell Z2 is a $20,000 system, and we're going to put down $5,000, and we're going to include in here a monthly payment that we'll try to make $200 a month. This APR, which is the annual percentage rate, is important, and in this we're going to put 0.05 because that's a kind of a common interest rate right now for things like that, and you would be very sensitive to changes in the annual percentage rate. The annual percentage rate is what we're told when we take out a loan, but the monthly version of it is what we're charged. So we have to take the annual percentage rate and divide it by the 12 monthly payments so that we can understand how much is added to each monthly payment of $200 on the it'll be a $15,000 loan. And in this case, that's simply, you just divide your annual percentage rate by 12. And when you divide by 12, you get this figure. So now we have our assumptions laid out for the loan. We can go back over to the first few columns and begin to punch in some of the data that we'll be using to calculate the total cost of the loan. So let's say that we're going to start this in January 2024. Be sure to enter the date like this, and then we can ask the computer to give us 20 years of months. So I'm going to highlight cell B2 and then the rest of the column all the way down to through 20 years of months. I've put an X at the bottom of this spreadsheet to keep me from sliding off the edge of the world there. And then we want to go to Home tab, click on the Fill button, and we want to fill down in a series, and it's a date, and we want it to go up 1 month each time. So this is what that dialog window should look like. and press OK, and now you see January, February, March, so on. Our loan that we're taking out will be for that $15,000. So we've had $20,000 minus the $5,000, that's Z2 minus AA2, and we should get a figure of $15,000 in cell C2. And next we just need to calculate the interest, and loans don't always work this way because sometimes the first and last months are peculiar in how things are done, and any of the banks would help you out by giving you a schedule of payments. But the interest is essentially the total amount of the loan times that monthly interest rate that we had. So it's equals C2 and then times, and then we have to go over and select the cell that has the monthly APR. Make sure you freeze that by pressing S4 so that there is a $ before the cell reference, both the column and the row reference. And so on a $15,000 loan at a APR of 5%, you'll pay $62 in interest on that first month. And so if you add these two, and then our payment is $200. Again, fix that or freeze that reference with an F4 key, or by typing the $ in, and it's $200. And so we'll do this simply to get the balance of payments, and that is $1,500 plus the interest rate minus our payment to get a new balance at the end of the month of $14,862.50. That amount is what you will start the subsequent month with. So you can reference the balance from the end of January to the beginning of February, and then copy these three cells one down, and you can begin to see how everything changes from month to month. And then you can just copy the entire 4 cells in row 3 all the way down to the bottom, and you will get eventually to a point here that it appears to be in the 92nd or 91st month, where you have only $22.68 plus the 9 remaining. And so your last payment would be in this month, and that would be for $22.68 plus the 9 cents, which would zero your balance out. And so here is the month at which you pay the loan off. And we could perhaps mark that by some other color. And 91 months is a little over 7.5 years. You can see now you're in July 1st of 2031 when the loan would be paid off. But in some ways, the loan will have been paid off far earlier than that, even despite a lot of the ups and downs that come with solar panels. So one of the next things we would want to do in this column is, this is our demand for electricity. And so in January, we use more electricity than average. And in July and August, we certainly do, especially here in California. And these numbers could be altered. The ones here, and I'll put them in bold, to suit different environmental or climatic conditions. But we want to repeat that for the entire 20 years of the program that we're trying to calculate. So in the January of the second year, press G2 and enter, and you have once again 111% of average monthly usage for January. But if you copy this all the way down, it will repeat this many times over, and then you can calculate your monthly demand a little more correctly. I'm going to press Control C to copy it and then paste it back as values, so that takes one of the formulas out and just replaces the number for with a standard value. The next thing that we want to do is to get the monthly demand in terms of kilowatt hours. So scroll over to the right, back to our assumptions. And this is the typical usage, energy usage of a house that I looked up online. And on the daily average, homes use about 30 kilowatt hours of energy. And if you multiply that by 365, you get almost 11,000 kilowatt hours. But then you take that number and divide it by 12, and so that is 912.5. And so we want to reference this number, 912.5, as our average monthly energy, and that's in cell AE17. So we can come back over here and type in AE17, the cell reference, and what we're going to do is multiply that by the monthly demand that we have that's accelerated in say January and July. So I've already put some conditional formatting on that, so we're above average for January. If you copy and paste this all the way to the bottom, and now we see that our monthly demand for kilowatt hours electricity is increased in July and August, and that's to be expected. It is lowered in the spring months, but some of the months where we get the most daylight, say in June, our average monthly might be slightly above average, but our generation, as we'll see, of electricity is going to be higher. So then we need to multiply our monthly demand against the cost of energy. And so that formula is our monthly demand multiplied by, and we'll come over here to our assumptions, the cost per kilowatt hour. This is highly variable depending on where you live, and it can be even more complicated in summer months where the kilowatt hours change at certain times of day or under peak demand. And so as complicated as this is, it could be far greater. So we're going to assume an average. I need to fix that by hitting F4 to put the dollar signs in place. And so our monthly electric bill would come out to $203. And I'm going to copy that all the way down through the rest of the column, and we will see that our bill goes up in summer. And of course, all of this can be adjusted to specific realities that you may face. One of the things that people fail to account for in these kind of calculations often is the effect of inflation. And energy prices have been going up at a rate of about 6% a year, according to one of the online sources that I looked at. In some places not so much. So we have calculated, or we'll assume, that there is a 3% increase per year, and that this is a monthly increase of 3% divided by 12. So of this very small number here. So we want to multiply the cost of the kilowatt hours by a monthly increase over the life of the solar panels.